This is problem 525 from the textbook. The text reads, determine the reactions on the bent rod, which is supported by a smooth surface at B and by a collar at A, which is fixed to the rod and is free to slide over the fixed incline rod. So we haven't done any, so with the, um, let's see, with the smooth end, oh, sorry, it just gives us that there'll just be a force that is perpendicular to that surface. So something like that. And then for sorry, the collar at A, if we go, so we're like, okay, I don't know what those reaction forces are. We just need to go and look at um, the table that Bala had uploaded, or look in your textbook at the table. And for a smooth collar, such as this one, you'll get a normal force, so normal to that direction. And then you also get a moment. Um, So I know I started drawing on that, but we'll actually draw a separate free body diagram. So let's do our free body diagram. So we have this. Um, and we'll draw our forces on there. So we have our NB. And this one is going to be perpendicular to that surface. And they tell us the surface is it goes over 12 and up 5 is the slope. Um, so instead it'll go over 5 and up 12. So 5, 12, and 13. So that's that common triangle. And then at A, we also have a normal force at A. And then the same thing, that slope for this line here is over 3 and down 4, 3, 4, 5. And so this one will be over 4 and up 3. So it's just perpendicular to that. So we have NA, NB, we have this 100-pound force here. And then we also have this moment here, it's 200 pound-feet. We need to put in all the dimensions. So we have 3 feet here, 3 feet here, and then 2 feet here. We already put the directions of those normal forces. And then we'll need to be finding an A. Oh, and then forgot the moment. We also have the moment about A. So we're going to find NA, MA, and NB. So just like normal, we have our 3 equations of equilibrium. Some of the moments about a point equals 0, some of the forces in the y direction equal 0, and some of the forces in the x direction equal to 0. Both NA and B have x and y components, so it'll make sense to start with the moment. So some of the moments about a point equals 0. Often I just pick the point that we know the least about. So I'll sum the moments about point A. Yeah, I guess with that moment we're going to end up with, it doesn't really matter. But so we'll do the sum of the moments about A equal to 0. And so the way I drew the moment at A is coming out of the board, so that would be positive. And we'll set that as positive. So we get MA. And then that 100-pound force, if we do our right-hand rule, it's going to give us a negative moment. So negative 100 pounds times 3 feet. And then we have that moment, which is in the negative direction. I just did the right-hand rule with that, but it's minus 200 pound-feet. And then we have that NB force, which will create a moment for us. And so we'll do, let's see, we'll need to break down that NB into 2 different components of its force. So basically just doing this. So we have the MB in the Y direction, and then MB in the X direction. The Y component of MB is just going to equal 12 over 13 times MB. And then the X component is just going to be 5 over 13 times MB. And so for our moment arm, or for our moment, we'll do that MBY, which is going to, if we do the right-hand rule, it's going to create a positive moment. So plus NBY. And then that moment arm is going to be basically this distance, which would be the 6 feet times 6 feet. And then we have NBX, which will give us a negative moment, so minus NBX. And that moment arm is going to be this here, that 2 feet. That's going to equal 0. So I'm going to rewrite that just with the MB. So MA minus 300 minus 200, so minus 500 pound-feet, plus MBY was at 12 over 13 times MB times 6 feet. And then minus an MBX was the 5 over 13 NB times 2 feet. That equals 0. Then we can multiply that out. Grab my calculator. And I'm just basically, we have too many unknowns, but I'm going to go ahead and simplify it. So I'm going to add these two MB terms together. So I did 12 over 13 times 6, and then minus that 5 over 13 times 2. And we get MA plus 4.7692. I just do a lot of numbers here. I'll actually keep using my calculator to make it a little bit more accurate, times MB, and then that equals that 500 pound-feet. So we have two unknowns. So let's move on. So we can sum the forces in the X direction equal to 0. And so the NA force, the X component of that is 4 over 5 times NA. The 100 pounds is in the Y direction. And then the MB does have an X component, which would be minus 5 over 13 times NB. That's going to equal 0. So we can rewrite that as NA equals 5 over 13 NB times 5 over 4. So we get NA equals 0.4808 NB. And then let's sum the forces in the Y direction equal to 0. So for that, go back to the free body diagram. We have that Y component of NA, so 3/5 NA. And then we have the 100 pounds pointed down, so minus 100 pounds. And then we have NB, or the Y component of NB, which is at 1213 MB. It's pointed up, so it's positive. That equals 0. And I'm going to plug this one into that. So we get 3/5 times 0.4808 NB plus 12/13 NB equals 100 pounds. I'm going to use my calculator. So we get NB equals 82.5 4 pounds. So that means we picked the right direction for NB, and then we can plug that into that equation for NA. So NA equals 0.4808 times 82.54 pounds. That equals, just grabbing those numbers from my calculator so I have a more accurate answer. We get 39.68 pounds for NA. And then the last thing is for that MA, for the moment, we need to plug it into this formula up here. So MA equals 500 minus 4.7692 times NB, so that's 82.54. And so that gives us, again, I'm going back up in the calculator to find those numbers. We get MA equal to 106 pound-feet. So this is a good one because it showed us how sometimes you can't simplify it to where it just has one unknown in one of those equations, but that's okay. We can just plug it back in. So those are our 3 answers here, here, and here.